Hello, everybody. Welcome to our machine learning seminar. Today, we'll have a pleasure to have a talk from Andres Felipe Calderon Hurtado, who is affiliated with a doctoral researcher in the School of Civil and Environmental Engineering at the University of New South Wales in Sydney, Australia. Andres, the virtual floor is yours. Please go ahead.
Okay, thank you so much, Professor Jakub. Can you hear me clearly?
Yes.
Okay, so yeah, thank you so much for your presentation. It's an honor to be here in your seminar. So as you mentioned, I am Andres Calderon, currently a PhD candidate at the University of New South Wales here in Sydney, Australia. And thank you everyone for attending this seminar. My background is in civil engineering, especially structural engineering. I did my master's here. And I'm currently, as I mentioned previously, a PhD candidate here. My supervisors are Dr. Mary Makialandari, Dr. Elena Troschenko, who I think is present in this seminar, and from Kyoto University, my supervisors, Professor Kim Shul Woo and Professor Chang from Kyoto University. So Professor Jakub, if you are okay with that, we can start the presentation now, or do you prefer?
Yes, please. A couple more minutes. Fully yours.
Okay, great. So today I will present some methodology that we've developed with our research team, which is an unsupervised computer vision-based approach for bridge damage assessment, applying drive-by bridge inspection. Just to start, by any means, I am an expert in machine learning. I'm open to any comments and suggestions from any of you at the end with your comments and questions. But yeah, here in our team, we think that machine learning, it's a great tool, powerful and useful for our research interest. That is, in my case, structural health monitoring of bridges. So the contents of today's presentation is this one. First, I'll go through a little bit of the background of what is drive-by bridge inspection and why we're interested in this. Then I'll present the algorithm that we use for this purpose. This, as I mentioned, this is an unsupervised learning algorithm, and I'll explain later why we prefer an unsupervised approach. And later, I'll present the methodology for damage assessment using this algorithm and some results that we already got from this methodology. And finally, I'll present some challenges that we've encountered and what's the future work in our research group. Okay, so the motivation for studying bridge health monitoring is that currently in the world are a large percentage of structures, especially bridges, have already completed their average expected service life. For example, in Australia, around 72% of bridges were built before 1976. So they have already completed their average expected service life. And also many of them, not only in Australia, but in the world, are considered effective. Approximately 40% of the bridges around the world are considered effective. So to this end, currently in the world, there are two main types of bridge inspection that are applied to bridges, any type of bridges. And the first one is visual inspection. This type of inspection of bridges is a very time-consuming task. And as you might imagine, this is very subjective to the inspector's criteria. Even though there are standards to doing this, it's still a subjective task. And again, it's a very time-consuming. On the other hand, we have conventional structural health monitoring systems. These systems involve the installation of many different types of sensors on the structure. which measure its response. And from the measure response, we can identify whether the structure is healthy in a healthy state or damaged. But the problem with these conventional structural health monitoring systems is that they are very expensive in terms of installation and maintenance. And as you can imagine, they are unique for each structure. So applying this technology to all the bridges in a country, it's a very would be like a very expensive task. So for this reason, during the last decade, researchers have studied this new alternative, which is called bridge drive-by inspection, which is an indirect structural health technique, monitoring technique. And this technique consists of an instrumented vehicle. Generally, it's instrumented with accelerometers. And this vehicle passes over the bridge, recording a signal, an acceleration signal, which has information from both the bridge and the vehicle. So this response has decoupled information from this combined system of the bridge and vehicle. And by studying this signal, we are able to identify whether, again, the bridge is damaged or not. So the advantage of this method is that it's much more cheaper than conventional structural health monitoring systems. And also, they have the ability to be extended to different structures. So those are the main advantages of this. However, there are still many challenges to cover with this technique, and today I'll cover some of them. Okay, so there are, when studying these signals recorded by the sensing vehicle, we can divide or classify these techniques into their level of damage assessment. So the level of damage assessment are three main levels. The first one is only damage identification. Level 2 is localization, and level 3 is quantification. Additionally, these techniques used to identify the signal from the vehicle can be classified into major groups. The first one is physics-based methodologies, which can reach up to level 2 of damage identification, that is localization. But these techniques require previous knowledge of the structure, such as the dynamical properties and other type of properties of the structure that we can compare with, that are taken as a benchmark state and then compared with other extracted features from the signal to assess the damage. So this knowledge of the structure is not always available. So this is a major drawback of physics-based methodologies. On the other hand, we have data-driven methodologies that can reach up to level 3 of damage assessment, so we can identify, locate, and quantify the damage. These methodologies are mainly focused on signal processing and supervised machine learning. However, as you might know already, if we are trying to use supervised machine learning, we would require information from all the bridge states. That means healthy states and damaged states of the structure, which is very difficult to obtain. Probably it's impossible to obtain information from damaged states. And so training these algorithms in real practice is not always useful. So this is the reason why in our research group, we try to focus on developing unsupervised learning approaches, which are mainly trained with benchmark states of the structure or healthy state of the structure. Okay, so now we'll talk about a little bit about the convolutional variational autoencoder. Some of you might have heard about it. So as I mentioned, with this algorithm, we intend to use an unsupervised method to identify damage. And this method should be only like feeded with healthy data of the bridge, because in real practice, that's what we can measure in real structures. So, okay, convolutional variational autoencoders or variational autoencoders are generative models used for unsupervised computer vision, and their aim is to reproduce images. So for the ones that are not very familiar with this topic, so I'll go through the three families. So first I'll go through what is an autoencoder. So an autoencoder is a type of neural network which aim is to reconstruct some input data um, and to deconstruct some input data into a low dimensional space. And from that dimensional space, try to remap that input data. So basically, we have an algorithm that is trying to reconstruct our input data. They are constructed with two parts, the encoder and the decoder. So the encoder task is to transfer the high dimensional input data to a lower dimensional representation. And in the other hand, the decoder tries to learn how to map the low dimensional data to the original input space. So now what is a variational autoencoder? So a variational encoder, it's similar to an autoencoder, but it adds a probability component to the latent space. The latent space is the low dimensional representation from which we want to reconstruct the original data. So the encoder learns to map the high dimensional input to a probability distribution of this latent space. Usually this probability distribution is a Gaussian distribution with a mean value and standard deviation. And later from this latent space, and which has a probability distribution, the decoder remaps this low dimensional space to the input space, trying to reconstruct the input data. And finally, what is a convolutional variational autoencoder? So usually variational autoencoders are built with fully connected layers in their encoder and decoder. So convolutional variational autoencoders are changing this encoder and decoder by convolutional neural networks, CNNs. And this is highly useful, as you might already know, for image processing. So these convolutional variational autoencoders are highly used in practice, and it's the state of the art for image generation in unsupervised computer vision. So it works in the same way. The encoder tries to map the high dimensional input to a low dimensional data with a probability distribution, and then the decoder remaps that low dimensional data to the original space. And what are the learnable parameters in this algorithm? Basically, they are the weights of the CNNs and the biases, and also the probability distribution of the latent space, which is basically a mean value and standard deviation. Okay, so next question is how do we train this neural network? So as I said, this algorithm tries to generate some input data. And to train this algorithm, we want to maximize the evident lower bound loss or the elbow loss function. So the elbow loss function is made out of two components. The first component is the reconstruction loss that basically measures the difference between the reconstructed and the original image, in our case, talking about images, and the Kullback-Leibler divergence. So this divergence measures the difference between the approximate posterior distribution and the prior distribution over these latent attributes. So in simple terms, the KL divergence measures how much the posterior distribution in this figure P deviates from the prior distribution Q. And the model is forced to learn a good distribution from the data over the latent variables and to capture like the relevant input features of the input data. So just to summarize very quickly how the CVAE works is like in simple terms. So the training data sets enters to the encoder. The encoder creates a low dimensional representation of the data, and then and which has a mean value and a standard deviation. Then the decoder takes that low dimensional data with probability distribution, sorry, and try to reconstruct the original data. And at the end, we compute the LD loss function, and we backpropagate all the gradients of the loss through the two CNNs, the encoder and decoder, and we update all the parameters. So this is how the training process works. Specifically for our project, this is the general architecture of the CVAE that we are using. So our input are color images of 224 by 224 pixels, and as you see here on the left, we reduce their dimension to basically a vector of 1 by 64, which has some probability, can be assigned with some probability distribution. And from here, with the decoder, which is also composed of convolutional layers, we try to reconstruct the same input space to obtain same size image. So this is the architecture that we use in our methodology. So let me now try to explain to you how we use this framework of the convolutional variational autoencoder into our damage assessment, breach damage assessment methodology. So let's first describe what is our problem, which is a numerical problem. So we are trying to identify damage in a breach, which in our numerical model is modeled as a simply supported Euler Bernoulli beam, and our sensing vehicle is a two-axis vehicle with 2 degrees of freedom. And we model the damage in the breach as flexural cracks using a simplified stiffness reduction method, and we model the cracks at the middle of the beam. Sorry. Later, I'll explain what are some challenges of the crack location for the damage location, because this is not only effective for flexural cracks, it can be extended to any other type of damages. But later, I'll explain what's one challenge that we have with the location of the crack. Additionally, the sampling process has some uncertainty. This uncertainty comes from the road profile. So we are modeling the road profile from based on the ISO standard, and this is an stochastic process. So this road profile adds a lot of uncertainty to the signal recorded by the vehicle, which later you'll see that adds a lot of noise to our signal, which makes it very difficult to identify the damage. Okay, so this is the pre-processing steps that we consider before taking our input data into the CVAE. So the processing of the data consists first of obtaining the axle acceleration of the vehicle. Those accelerometers are placed in the suspension of the vehicle, so we obtain the acceleration signals from there. The second step is to align the signals, because since this is a two-axle vehicle, the first step is to align in space the signals, so that the signals are aligned from the moment each axle enters the beams and to the moment each axle exits the bridge. The second step in our processing step is to calculate the continuous wavelet transform, which is a time frequency domain representation of signals. And we do this for both axes, from the acceleration from the front and rear axle. The third step is to calculate the residual CWT. And what is this residual? CWT is the difference or the subtraction of the CWT from each of the axes. The reason why we do this is because we notice, and it has been reported in other literature, that this process can reduce, partially reduce the effect of the road roughness in the acceleration signal that we measure. However, there are still some noises due to this fact. So to further remove the effect of road roughness, the last step is to do some image averaging. And this step is very important. Here we don't do the averaging over the CWTs. We do the averaging over the images. And the reason is because for every sample, the values of the CWTs are different. But when we use these color images, we normalize these values. And when we take the average, we already take the average over normalized data. So these are the four pre-processing steps that we consider. And for modeling damage, we considered three damage scenarios. So cracks with 10% crack, 20% cracks, and 30% crack. This percentage is the crack depth to beam height ratio. So these are the three damage cases that we consider in our numerical study. So how the training and testing process happens in our methodology. So we generated 400 samples of the vehicle passing over healthy states. Again, these samples are all different from each other because at each run of the vehicle over the bridge, we consider that the road roughness is different. So these samples are all different, and the signals obtained from them are all different. So basically, the algorithm is learning to reproduce only images, CWT images from the healthy state. So what we are expecting is that when we introduce an image from a damaged state, the algorithm cannot properly regenerate that image. So for testing, we are taking 100 samples from each of the bridge condition, including healthy and the three damage cases, and we define a damage index, which for this specific study is the root mean square error between the reconstructed image and the original image. So what we expect is that the larger the damage, the larger the root mean square error, the error between the reconstructed image and the original image. And eventually that would be an indicator of the severity of damage, which I would show in the next slide. So these are some results that we got from our numerical experiments. And here I wanted to compare three different results from three different type of inputs to the algorithm. And this is to show the importance of the pre-processing steps in our methodology. So in the left figure, you can see the results of the algorithm when it was trained only with the CWTs from the acceleration signals of the front and rear axles only. So you can see here that it is very difficult to identify whether the bridge is damaged or not. And also for the damage cases BCM1, BCM2, and BCM3, all the damage indexes are the same, so we cannot clearly identify the severity of damage. Similar results we see in the when the convolutional variational autoencoders are trained with the residual CWT. As I mentioned previously, this is because even after taking the residual CWT, there are still some uncertainties in the signal. And on the very right figure, you see that by averaging, we reduce further those uncertainties. So we can clearly define the three differentiate the three damage cases from the healthy state. And we can also differ from all three different damage scenarios. So this damage index could be used as a quantification measurement of the damage, and also an identification measurement of damage. So we can, with this, we can identify and quantify the damage, as I mentioned in the initial part of the presentation. So even though this methodology have shown some like promising results, because not many people have used unsupervised learning methods for breach damage assessment using drive-by inspection, there are still some challenges which justify our future work in this field in our research group. So the first challenge, as I mentioned at the beginning, is localization of damage. So currently, we are working with CWTs for the time frequency domain representation of the signal. But what happens when we have damage at different locations is that we might affect different modes of the structure. And this means that our frequency range in our CWT should change. So maybe we need to study a high frequency range and specifically for the CWT, the resolution reduces when we increase the frequency range. And so it gets difficult to identify the change in natural frequencies of the breach when we affect different modes. Also, many studies in the past have reported that all these methodologies for breach damage assessment perform better when the vehicle speed is low. So in some real cases, this is very challenging to obtain in real bridges because they are high-speed bridges. And sensing the bridges with low-speed vehicles, it's another challenge that has to be studied further. And lastly, the noisier signals can also reduce the performance of the algorithm. These noisier signals can come from rougher road profiles, or when the signal is very noisy, purely from the measurement noise. So our future work in our research group is to identify a better feature to locate damage, maybe different time frequency domain representation, different than the CWT. The next step that we're working on already is the vehicle optimization, the properties of the vehicle, like the suspension, mass, and all this, because there's an important fact that is that different vehicle configurations can perform better than others. So a vehicle optimization is needed for this. And finally, we want to test all this framework of breach damage assessment in real life scenarios, especially in a cable stayed breach here in New South Wales, to which we have access. And we have an autonomous electric vehicle, which is on the left, which is has 4 accelerometers, and currently we are installing some load cells as sensors as well. And yeah, this is the future experimental studies that we are planning to perform to test all our framework. So yeah, that's it for our presentation. This is our methodology for breach damage assessment. This is our project. I hope you enjoy it and found it interesting. And I'm very happy to answer all your questions, comments, suggestions And yeah, thank you so much for your attention.
Thank you, Andres. Let's move to the discussion part. Again, as usually, whoever has a question, just raise your hand or switch on your mic, start asking questions, or use the chat. We have several questions as well. So maybe let's start. So indeed, it was a very thought-provoking presentation, and I liked the fact that you use these stochastic autoencoders that I'm a bit familiar with because of our work with SORAP, who is also here with us. My question is a bit more general question about the sensitivity of those measurements, because the bridge is very big, right, and very stiff, while the car that holds the measurement device, or is a part of the measurement device, I better say, is more light, especially this small electric car that you showed in the end of the presentation. So its interaction with the bridge is very limited. So it doesn't induce too much vibration to the bridge, right? And on the other hand, it has its own suspension system, its own complex mechanics in between the measurement device, meaning the accelerometer, and the contact with the bridge, and maybe the faulty part, which is even further hidden in the bridge.
Yes.
So my question is, what sort of accuracy of the measurement you need to have, and what sort of sensitivity of your measurement is with respect to all those parameters, and then the noise and other sorts of uncertainty that can happen in between. So have you had any analysis or study on that? What are the let's say minimum mass of the car that versus the stiffness of the bridge that you have to consider to have it properly set up?
Yeah, thank you for your questions. Those are very, very important questions that have been asked over the literature many times. So to answer the first question about the sensitivity is, since we are using an unsupervised method, it's difficult to define where's the limit. From the testing using this methodology with I mean, if we test the methodology with all healthy samples, we could define a threshold from those reconstructed images to define where's the limit when we can say, okay, the bridge is damaged or not. But here comes a question that we have been trying to answer, and also that limit depends on the type of damage. So we found that this methodology is not very sensitive to very low damage scenarios. Like when in this numerical study, when we have very low severity cracks, these cracks reduce the dynamical properties of the bridge in a very minimum quantity. So identifying these small changes with a system, with a feature that is not that doesn't have like an adequate resolution, leads to not good performance in identifying this damage. So to answer this, yes, it is not sensitive to low severity damage, and for this purpose, we are working on introducing other features that have better resolution both in time and frequency. In time and frequency domain. To answer the second question, yes, there is it is very important, and thank you for noticing that. Our vehicle, our sensing vehicle is probably, when sensing, is for sure not going to excite the bridge in the sense that we want to extract the bridge properties. So to do this, many other researchers, and what we plan to do is to apply some external excitation to the bridge. That could be adding external traffic or doing the sensing while traffic is going on, so that we can excite the bridge while the sensing vehicle is passing over it. So basically, we are treating the sensing vehicle purely as a sensor and not as an exciter. The exciter will be something different. Either like external excitation, it could be, I don't know, a hammer, or external traffic, as I mentioned, so that we can extract bridge properties. And also, to answer the second part of your question regarding the vehicle properties, yes, there is, we want to cover that topic with our vehicle optimization framework. Someone could ask, okay, but how can you do the optimization of a vehicle that doesn't have like a big range of alternatives to change? Okay, yeah, that's also a valid question. But we want to create like this framework to set some guidelines to define what are the vehicle properties that are more suitable for a specific bridge. And we want to relate those vehicle properties with the bridge properties. For example, the mass of the vehicle and the mass of the bridge. We want to reproduce some guidelines in the relation of the masses, or maybe the relation of the stiffnesses. But in general, what we want is that the vehicle natural frequency is different from the bridge natural frequency. And what we also want is that the mass of the vehicle is significantly less than the mass of the vehicle. Those are some general guidelines for the vehicle selection. And yeah, I think that's the answer to your questions.
Yes, thank you so much. It was not very focused on the very topic on the, my question was not very focused on the topic on the seminar, but a bit related through the, let's say, data-driven part and
Yes.
modeling part. So may I ask a second question? Taking the opportunity that there is no question, no raised hand. Oh, there is some chat entry. It is your supervisor, Elena Trashenko, who sent the link to your paper on that topic, right?
Okay, thank you so much.
So let me ask a question about the neural network model, the deep learning model that you are using. It is a stochastic model, right? So
Yes.
variational base for this sort of model. But I was not sure what was exactly the model built, how it was built. Because you had this, can you show maybe the slide, one of the first slides in which you showed the architecture of your neural network? Like something like this. And you have this encoder. Okay,
maybe
it was
this
good.
one explains better.
No, this one is good. The schematics.
Yeah.
So you have this encoder part.
Oh, sorry. sorry.
Okay, this one is good. So you have this encoder part. Then you have some latent layer or latent neurons. And then you have the decoder part. And my first question is, and this is the autoencoder setup, right? So you are aiming to have the same input and output. That's your that's your ROS function.
That's the aim.
Mm-hmm.
Yes.
So, and then you mentioned that you have the stochastic part of your neural network is the latent
yes.
part, right? So how do you understand it? This is my first question. Whether the stochastic parameters are the weights or the neurons themselves, the values. What's your stochasticity?
Those are the values. Because that's how I understand it, is that's the difference from a variational autoencoder to an autoencoder. An autoencoder just generates this low dimensional output from the input, and purely from that low dimensional, you pass it through the decoder and try to reconstruct the image. However, in the variational autoencoder, this latent variable, this low dimensional space, is low dimensional data after the encoder, is assigned with some probability distribution. For our case, a Gaussian distribution. So this is also a learnable, and this mean value. And so we want to create this probability distribution that represents our input, our big input data set in the latent space. So we assign a probability distribution to this latent space, and that becomes also a learnable. Those variables.
Okay, I'm not fully sure if I understand the approach, because let's say you want to retrieve the perfect data, right? But you have a model in between that compress the data and then decompress, and it is not a perfect compression decompression, meaning that you have some error that you're adding, right? And which is expressed by the loss function in the end. But on the other hand, you have some stochastic parameters in the latent space. This is my another question. What are they and how they are, let's say, implemented? And now, what's the let's say training process there? That is, so how do you interpret this stochasticity? The mean value is more or less obvious, but the standard deviation, what does it express? What is the interpretation of the standard deviation in your model?
Okay, as I mentioned at the beginning, I'm not an expert on this. So how I see it is that our input data, as with any type of input data, has a lot of uncertainties. So adding these stochastic variables helps the algorithm to generate all these uncertainties in the input images. That's how I see it. So we have our input data, and it has some distribution because all of its uncertainties. So it has some probability distribution in this latent space, this low dimensional space, and that helps reproduce the output more accurately, I would say, because we can consider these uncertainties from our inputs data.
Okay, but do you have any slide that is showing how those stochastic parameters are introduced in the whole framework? Or maybe Saurabh can help on that.
No, sorry, unfortunately, I don't have that.
Hi, Trey. This is Saurabh here. Nice presentation, by the way. Thanks for that. So to answer Jakub's question, Jakub, in the latent space, first you actually have, let's say, two nodes, which one represents the mean and one represents the standard deviation. And you also have to use this reparameterization trick because you cannot have the back propagation for the sampled variable. So these are the three components in the latent space.
But these are the nodes, right? These are not parameters of the model.
No, these are nodes. These are not parameters of the models. These are the nodes. So
Okay.
the parameters of the models are deterministic here, but just that you have one node that represents mean and one node represents standard deviation, and then you create a sample using those two values, which is mean plus some scaling into standard deviation, something like that.
I see. So for a given input, you can quantize somehow the uncertainty around that input point.
Yeah. So how actually variational autoencoders use this? Once it's trained, now you take out the encoder part, and now you just have the distribution, that is mean and standard deviation, and you just sample something from there, and it generates a different output. Every sample generates a different output.
But also for a given input, you can generate the stochastic parameter around that input data.
So, to my understanding, variational autoencoders are not really used to capture the uncertainty because I'm not sure the simple distribution is able to do that. Like you have Bayesian neural networks, you have this where parameters as distribution over all the layers, and those are more effective than these kind of approaches for tracking the uncertainty. So it's a bit different concept. As Andre mentioned, it's used for generative purposes, is to generate different outputs from some sample distributions in the latent space.
Okay.
Yeah, thanks so much. Maybe that was more clear. Also, I'm a little bit more clear as well.
Thank you. Yeah, but the one important thing I think it has to be discussed here is the reparameterization trick. That's important in the training procedure. Yeah.
Okay. And let's say, let me see whether there's any question. No. So just to have a very small follow up. So how this framework, once you have it, this unsupervised autoencoder framework with this stochastic capabilities, how is it then used in the in this detection in the damage to compute the damage index? Because either I missed it in the presentation, or I was taking some notes maybe, and in that time you mentioned about it, but I didn't get the idea how this framework, the neural network framework or deep learning framework, how is it then used in the identification process? This was not clear.
Okay, so as I mentioned, so the training process is basically performed using only images like CWTs as here from the healthy state. So basically, the algorithm learns to reproduce images only from this state. So the way that we use it for damage identification is that when we input a CWT that is somehow different from the inputs that we use for training, the reconstructed error between the reconstruction error is increased. So we use this error as a damage indicator for us. So just a simple case here, you see here in this row that in the residual CWT, this yellow dot represents the change in natural frequency due to damage. So basically, we are training the algorithm to identify this, like in technical terms, like identify the or reproduce CWTs with the same natural frequency as in the first image on the left. But when some images have a different natural frequency, then the algorithm cannot regenerate this image, and then the reconstruction error increases. And that's our damage indicator, and that's how we use it.
So you need to have a healthy model for each bridge, more or less.
Yes, exactly. So in practice, yes, exactly. So in practice, we wouldn't call it a healthy bridge. We will call it a benchmark bridge, because from the starting point, we don't really know if the bridge is healthy or not, but we will consider that as our benchmark. And the data from that benchmark state will be then used for training, and any change in the signal representation representing bridge changes in the dynamical properties of the bridge will be identified based on that benchmark state, which for the numerical case, yes, it's the healthy state.
Okay, I see the point. And how can you know that the model cannot perform well for the damage bridge? Because this is it's a crucial point for your measurements. Is the assumption that if you have different frequency profile, the model will give a higher error
Yes.
encoding, decoding, right? So how can you be sure that the model will not extrapolate or interpolate the data for the damaged bridge?
Yeah, that's a very important question. Like there's a trade-off for low severity damage. So when we have damage, okay, so two important things about the vehicle bridge interaction system. So when vehicles cross over the bridge, the coupled system has a combined natural frequency, which is not the same as the. But when you analyze the spectrum of the signal, you can identify the real natural frequency and the combined natural frequency, which is called the deviated natural frequencies of the bridge. So this can be further improved by doing some more signal processing, like signal decomposition methods, to extract the exact components of the signal that represent only the bridge components. That's a difficult task to decompose the signals, but yeah, there's always a trade-off because we cannot identify all the minimum changes in the bridge natural frequency. That's a very difficult task. And yeah, as I mentioned, there are still some future work to do in that regard. But for like what we want to show also is that for relatively medium to large damage, we can clearly identify the change in with this methodology.
I see. Thank you so much.
Thank you so much for attention. I hope it was useful.
Yes, I can see no more questions now. Well, thank you again, Andres, for a very nice presentation and for answering our questions, and for your effort to prepare everything. Have a good evening to you and have a good day to everybody who is closer to my time zone. I will keep you posted about the future seminars.
Thank you so much, Professor Jakub, and everyone for attending. Thank you so much.
Bye-bye.